Welcome to 5-Minute Papers on AI for the Planet. I'm Grace Lindsay. Today we're reading Deep Solar 3M, an AI-enabled solar PV database documenting 3 million systems across the US. Let's get started. It's a well-known fact that in order to stave off the worst effects of climate change, the world needs to switch entirely to low-emission sources of energy. Solar power is a great example. It's a cheap and abundant resource, and its use has been rising across the globe. It's responsible for up to 30% of the energy supply in some countries. However, solar energy use is not evenly distributed, and even keeping track of who is using solar and where is not so straightforward. Solar energy can come from industrial-scale solar farms that send their energy through the power grid into homes and businesses. Or it can come from rooftop solar panels that power a home directly without any interaction with the power grid. When it comes to residential solar, homeowners can simply hire a solar panel installer or even do it themselves, which is great for getting more people to use solar power, but not so great for tracking our progress on it. And that's where the methodology in this paper comes in. It utilizes the fact that you can't hide solar panels. If they're on your roof, we can see them, and we can even see them from space. So this paper uses satellite imagery to create a map of rooftop solar panels across the US. The imagery used is accessed through the Google Maps API, which curates a collection of high-quality satellite imagery spanning the globe. This imagery has a resolution of around 15 to 30 centimeters per pixel, which is good for being able to see solar panels, which are usually only about a meter long. But the goal here is to map residential solar across the whole US. Collecting imagery at this resolution for the whole country would result in over 1 billion images to process. Luckily, there's a smarter way. Specifically, the authors use the Microsoft Maps dataset of buildings to restrict their analysis just to rooftops, leaving them with 230 million images to analyze, each representing about 50 meters squared. The images then go through a 3-step processing pipeline. The first step is to detect if a solar panel is present or not. To build a model that can do this, the authors start with a well-known vision transformer model that was trained to classify objects in images. They then use a trick called low-rank adaptation, or LoRa, to efficiently update parts of this model to make it specialized for detecting solar panels. If a solar panel is detected in an image, it then moves on to the next stage of processing, where its size and type are analyzed. To determine the size of the panel, the authors need to perform segmentation, meaning they need to find and outline the panel's shape in the image. Here again, they start with a model, this time the SegFormer model, that was pre-built to segment objects in images. They then fine-tune it to be good at segmenting solar panels in particular. Finally, a separate object recognition model is fine-tuned to classify the type of solar panel, for example, residential versus commercial. Using this pipeline, the authors identified almost 3 million solar panel installations across the US, with the large majority of them being residential solar. By comparing the current data to a 2017 solar survey, the authors noted that the number of solar panels has more than doubled over a 5-year period. Looking state by state, California continues to lead in panel installations, but Texas is the state that saw the highest percentage of growth since 2017. The authors also note some interesting patterns in how the panels are distributed. For example, the density of solar panels doesn't scale with the density of people. Rather, solar panel use peaks in semi-urban areas and decreases in more urban ones. They also find that solar panel use increases with household income and median age of a region. It is also slightly influenced by education level. But this data doesn't just let us understand where solar panels are now. It lets us plan for how they should be deployed in the future. To this end, the authors also gather data via the NASA Power API about how much solar energy a location receives from the sun. They use this to identify regions particularly well suited for getting power from the sun, but that don't have many solar panels at this moment. These areas should be high priority for community solar projects and other incentives for getting solar panels installed. The authors highlight that this is the most complete and comprehensive data set of solar panels in the US, and they make it publicly available along with all the models that they built to process the imagery. Overall, this work really exemplifies how an ecosystem of large open data sets and models can be utilized to create new insights and directly influence policymakers. That's all for this paper, and remember to subscribe to this channel if you want to see more examples of how AI and machine learning can be used to understand and protect our planet.